Welcome to the ICS 211 lecture on collections and linked list. This is a summary of the linked list abstract data type, our first abstract data type this semester. So what is the Java collections framework? It is a set of interfaces and classes that provide collections of items and different kinds of collections of items for Java. It starts off with the iterable interface, which provides an iterator to traverse or loop through all the items in the collection. It defines a collection interface. It provides some fundamental operations on all collections. And there are sub-interfaces that define the different kinds of abstract data types, such as lists, queues, and sets. There are also abstract collection classes, base class, which is abstract for all collections. In the example that we've talked about recently, the abstract list provides a base class for all the Java lists, and Java provides two different implementations of the linked list, of the list class, a linked version and an ArrayList, which have different performance properties. So what is the collection interface? The collection interface is a public interface. It extends iterable and provides a bunch of methods. Here are some that are important. You have the ability to add an element to the collection, so you can increase the size of the collection. You can ask the question whether or not a collection contains a particular object. If it does, it will return true. If it does not, it returns false. You can get an iterator over all the items in the collection, so you can loop through all the items in the collection. You can ask the question, how many items are in the collection? You can also remove an object from the collection. The first abstract data type that we'll discuss this semester is a list, which is a collection that provides the addition of having an order. So there's a first item, a second item, a third item, a fourth item, etc. Lists do not have gaps in them. So if you remove an item from the list, the items below it or to the right of it, or however you think of it, shift up. So if you remove the second item, the third item becomes the second item, the fourth becomes the third, etc., etc., etc. So what does the list interface look like? In Java, it's a public interface list. It's a generic list, so you can instantiate it with a different class type, and it provides a set of it overrides or extends the collection interface. So it provides all the methods, or defines all the methods in the collection. So we have the add, the contains, the iterator, the size, etc., etc., etc. And it also provides the concept of a position or an index of the items in that collection. So you can ask the question of, get me, what is the item at the third position in your list? You can replace or set the item. This is not insertion, this is replacing the third item or the second item. If the list is not large enough, this will throw an index out of bounds exception. So we can replace the second item by calling this method with index of 1. All lists in Java are zero-based indexing. We can ask the question of where in the list does this object occur, which is slightly different than does this list contain or have this item. We want to say where in the list is this object. We can remove an item at a particular index, saying I don't like the first thing or the second thing, and it will be removed, and all the items that are at an index greater than that, their index is reduced by 1 because there are no gaps in lists. And we can add into the middle of a array or a list by saying I want to add at this index, which will then shift all the items with an index greater than or equal to the given index, will increase it by 1. So we'll shift them either down or to the right, depending how you picture your lists in your mind. So we talked about 3 different implementations this semester of the list interface. The first one we talked about is the ArrayList, which you can see the ArrayList extends the abstract list class and implements the list interface. It's an array list because we store the data in an array. So we keep an array called data that holds all the elements in the list. Now the length of the data array is always going to be greater than or equal to the size of the list. So we need to keep track of the size of the list. We have an add element that in the collections interface, you just add it to the collection. Well, in the list, we add it to the end of the list. And in the case of the ArrayList implementation, we just assign the element to the array at size, increment the size, and then we're done with the operation, unless there's not enough room in the data array so that we need to reallocate a new data array that is larger and copy the old data array and then just insert the item into size and increment size. We ask the question it contains, so we just search from 0 to size whether or not the object is in the array. Return true if it is. We have an iterator. We return an iterator, and in this case we can return a list iterator because we have an array. We just keep track of what position in the array we are. So we can ask, is there a previous node or a previous item in the array? Well, if the position is not 0, we can go to the left and decrease its position, or we could go greater than. As long as the position's not at size, we can always say, yes, there is an item to the right of that, so we can return a list iterator instead of just a regular old iterator which only has next. So we can return a list iterator which has next and previous. We just return the size. This is a big O of 1 operation because we remember the size. Get it index is a big O of 1 operation because we check the bounds on the index and then just return the item in the array at that index. Set, same thing. We check the bounds on the index. We remember the value in the data array at that position. We then replace it with element and we return the old value. Index of, again, we have to search the array from 0 to size to see if object's in there. If we find it, we return that position where we are. Remove, we just have to shift all the items in the array from index plus 1 to size, 1 to the left or 1 smaller. So we take index plus 1 and move it to index plus 2 to index plus 1, etc., etc. Big O of n operation because we have to shift all the items in the array to 1 smaller index. Add, similarly, we need to create space in the array at index, so we need to shift all the items from index to size, 1 greater index, and then we can insert the element at index. So that's a big O of n operation. The second implementation we talked about is, instead of using an array, we have a singularly linked list, or we have a node that stores the information. So again, you can see the singularly linked list class extends abstract list and implements the list interface. In this case, we need a private class to define the node that holds each element. And in the singularly linked list node class, we have just a pointer to the next item in the list. We just know what the data is and what's next. Now, in order for the class to work, we need to know what the beginning of the list is, so we have a pointer to the head, the beginning of the list. We also have a pointer to the tail, or the end of the list. This allows us to add an element at the end very quickly by just setting it up. I'll talk about that very shortly. We also remember the size so that we don't have to keep counting how many nodes we have in order to return the size. This just improves our performance. Boolean add an element at the end of the list. We just create a new node, set its value to element, point tail.next to it, and then set tail to this new node. And we are done. Big O of 1 operation. Contains, we need to traverse the entire list, so we start at head and just going next until we get to the end of the list. If the object is in there, we have to keep track, or we can return true. Iterator, in this case, because we have a singularly linked list, we cannot go backwards. We don't know the previous, so we have to return just a regular old iterator that provides has next and next operations. Return the size of the list, just return the private member variable size. Get, we need to keep track, we gotta go next, index times, return that value. We can't check the bounds. If we fall off the end of the list, we can throw a index out of bounds exception. But we don't know how long, we can check it against size. But we need to check the bounds and then we can traverse. Again, because we're traversing the big O of n operation. Set, check the bounds against size, and then we have to traverse, and then we just insert the node insert the element by creating a new node. We go to index minus one node, create a new node, set up the new node's pointer to be index minus one node's next pointer, and then set index minus one node's pointer to the new node, and we've inserted it. The actual insertion is a big O of 1 operation, but because we have to traverse to index, that's a big O of n operation. Index of, start at the head, count how many nexts we call until we find it, return that number. Big O of n operation. Remove, again, we traverse, check the index, traverse the right number of times, and then we just index minus one times, and then we just update the pointers, which will skip out of the node that we're getting to. Remember its value before we do it, and then return the old value. Add, again, we traverse to index minus one, create a new node, set up the pointers, but since we traversed all these methods with the positions are big O of n because we have to traverse to index. The second implementation was a doubly linked list, which is very similar to the singly linked list. The difference is our inner node class now has a previous pointer. So each node knows who's next in the list and who's previous in the list or before them. Again, we keep track of the head, that's the beginning of the list. Keep track of the tail to make it easy to insert at the end. We keep track of the size so that we don't have to count the number of nodes every time. Add an element, we just add a new node at the end at tail, move tail, increment size, big O of 1. Contains, we can start at tail or we can start at head and traverse forwards or traverse backwards, it doesn't matter. If we find it, we return true. In this case, because we can go backwards, we can return a list iterator, so we can go forwards or backwards through the list. Size, we return the size, the private member variable. Get at index, we check its bounds based on the size. We can traverse forwards or we can traverse backwards, it doesn't really matter. I find it simpler to traverse forwards, I like counting up instead of subtracting from size. Return the value. Set, again, we check the bounds, we traverse forwards or backwards, and then replace the element. Index of, excuse me, we start at the beginning or start at the end, traverse forwards or backwards, looking for the item, keeping track of where we are, return the index if we find it, return -1 if we don't. Remove, traverse forwards, and then remove the node by changing the previous and the next pointers appropriately. Add, again, traverse to the index, create a new node, set up the pointers. All of these are big O of n operations because we're traversing the lists. So let's compare the big O of an array list implementation with linked list. Get and set for the array list are big O of 1 because we just grab the value out of the array. For the linked list, we have to traverse to get there, so big O of n for them. Index of, both cases we have to search the list, so that's big O of n. Remove, for the array list case, we have to shift all the items to the left or one less in their index. In the linked list, we have to traverse to index, so that's why they're both big O of n. Size, we just remember the value. Add, at the end, if we have the tail pointer, they're both big O of 1. Add in the middle, for the array list, we have to shift all the items one more index. And for the linked list, we have to traverse. So the comparison is basically the get and set methods are quicker for the array list and the rest are the same. Thank you very much.